Okay, starting chapter 3 here, we are beginning with but graphing linear equations. So we have three things to talk about in this section. The first one will be plotting ordered pairs, because anytime we graph, we need to start with the basics and plot ordered pairs. The second thing is determining if an ordered pair, when is an ordered pair? Ordered pair, a solution to an equation. And lastly, we will be looking at graphing linear equations. Equations with a U. Okay, so we can't talk about graphing without talking about the Cartesian coordinate system. So this has a couple different names. You've probably heard most of these. The Cartesian plane, the rectangular plane, the XY axis. Most of the time I'll just call this the plane. It is the surface of your paper. It's two-dimensional. I have these axes here that you can use as an example, and we always plot as an ordered pair each point with an X component and a Y component. And so when you see the word or hear me say the word component, I'm referring to one of the pieces of the ordered pair. You can swap out ordered pair for point. They refer to the whole thing written like this. Now, this is the part of the section where I remind you that mathematicians are lazy. As you'll know, we're using parentheses here for ordered pair, and that is the same notation for an interval, an open interval. Unfortunately, we like to reuse notations in math. One of the worst ones you'll ever come across is zero. Zero means a lot of different things depending on what math class, math topic you're talking about. And parentheses are another one of those things where you're going to see them over and over and over again for a lot of different things. So we want to make sure that we understand when we're talking about an interval like this or an ordered pair. In this section, we're talking about ordered pairs. So the next definition we need to talk about is linear equations in two variables. So we saw in the last chapter linear equations in one variable, but a linear equation in two variables is an equation that can be written in the following form. It looks like ax plus by equals c, where a, b, and c are all real numbers, and a and b cannot both be 0, but one of them could be 0. So we lessen that restriction from the last time. And this is called the standard form of a line. So a linear equation is a line. That is what its graph is going to look like. So we're going to take this step by step. We're going to start with just plotting some ordered pairs and then looking at ordered pairs when they're solutions, when they're not solutions, and then we'll get to back to the equations. So in this example, if we're going to graph, we need some axes. So I need to scale my axes. Scaling your axes is very important. Make sure you get enough points, enough tick marks, and make sure that it's scaled properly. You don't want to be too liberal with how you scale your axes. And when I say scale, I mean when you put tick marks in like this. How many I get there? 1, 2, 3, 4, 5, 6, 7. I have 8 of them there. Now, I can make this 1 to 8. I can make this 1 to 4. I could make this, 3 to 24. It all depends on what I do. So just putting tick marks here, you need to label them. At the very least, every other one. So I'm actually going to do 1, 2, 3, and 4. And this is going to allow me to give some half marks. And since I have 1.5 and negative 1/2 here, that's kind of why I decided to do that. And I'm going to mirror it on the other side. 6, 7, 8. And this is going to be negative 1, negative 2, negative 3, negative 4. And then on my up axes, 1, 2, 3, 4, 5, I'm going to go strictly by ones. So notice I'm not doing in the in-betweens. If this is 1 and this is 3, then this tick mark in between has to be 2. And that's how we read that. This will be -1, -3, -5. And so these are well-scaled axes. Now this is about as different as you want to be. Notice I have 2 different scales on my x and y axes. The x-axes are scaled by half, 1/2, 1 1/2, 1, 1.52, 2.5. But on my y-axis, I'm only scaled by ones. You don't want to go too much more than that because you can start to, what we say is, distort your image when we get to graphing equations. So if you're going to have 2 different scales on your axes, make sure that they are close, about 1 digit apart. If you're scaling by 3s, then you want to be scaling by at least 2s on your other axes, and as most as 4s. That's something you'll get used to as you start graphing more. So now I have the axes. We're just going to plot these points. So starting with point A, 2, -1. So 1, 2, -1. That's down here. And we always label our points so that I don't have to guess. Obviously, I covered up my scale there, and that happens when you're graphing by hand. So now the reader doesn't need to guess what this point is supposed to be because I've labeled it. Point B is 0, 5, so that's 0 on the x, and then 5. Again, make sure you label. There doesn't need to be any guesswork involved. And then C is -3, 5, so that's up here. And my patented form of, if you make a mistake like I just did and my point looked funny, just make your points bigger. So if this looks funny to you, you just make your point bigger. If this looks funny, you just make your point bigger. And that's another reason why we label our points, because we can't physically put the point perfectly where it needs to go because we're using pens and pencils. So always label your points. The next one is -2, 0. That's right here. The next one is -1/2, and then -4. So this is a good example. If we look, I'm not perfectly straight on the -4, and I don't need to be because I'm going to label this. And you're not going to have to guess what that's supposed to be because I've told you what it is. And then finally 1.5, 1.5. So now here is where we want to be close as we can. So in between 1 and 2, halfway, and then out about here. So that's going to be something like that. And again, this isn't going to be perfect because I'm not a perfect human, and I don't expect you to be either. But I'm going to label it so you don't have to guess. So even if it looks like I'm at 1.7 on the y-axis, I've labeled it 1.5 so you know it's supposed to be 1.5. Okay, so big takeaway here, make sure you are labeling your points when you plot them. Alright, so this next example is about determining when points are solutions. So we have 3 points, 0, -12, 1, 9, and 2, -6. And we have this equation, 3x minus y equals 12. So determining if something is a solution is as simple as taking the individual components, the x and the y, and swapping them in or substituting them in to your equation. So this first one would be 3 times 0 minus a -12 should equal 12. 0 plus 12 equals 12. Yes, it does. So the yes, this is a solution. For the next one, we have 3 times 1 minus 9 should equal 12. Is 3 minus 9 equal to 12? That's a no, so this is false, which means that no, this is not a solution. And then finally, 3 times 2 minus a -6 should equal 12. 3 times 2 is 6, minus -6 is plus 6, and 6 plus 6 is 12. So this, yes, is a solution. So when you're determining if a point is a solution, it's as simple as plugging in those components back into your equation and simplifying. And you want to make sure that you end up with a true statement here. So we turn the page. now we are graphing. So here we are graphing the equation 3x minus y equals 12. So I'm going to rewrite this by adding y and subtracting 12 to either side. So I can get it as y equals 3x minus 12. So this was standard form that we are given. And you can use standard form, but it's a little bit more effort. When we're graphing, we're going to talk about this form in more detail in the next section. This is slope-intercept form as a little hint. Now, a lot of you probably know slope-intercept form. When we're graphing, we want to pick x's and y's to plug in. You should pick a couple points. I like -1, 0, and 1 for my x's. And this is why we solve for y, because now plugging in these points is easy. So when I plug in -1, I have -3 minus 12 equals -15. That gives me the point -1, -15. When I plug in 0, this term disappears and I just have -12. And when I plug in 1, I have 3 minus 12, which equals -9. So I have 3 points to plot, 0, -12 here, and 1, -9. So these are the 3 points we're going to make our line out of. And when we're choosing axes, I supplied the last ones, but you can customize your axes to the points you have. So I don't need the same exact axes that we had before back here. I don't need those guys because I mostly have big negatives to plot on the y side. I don't need any positives. So when I draw my axes, I'm going to draw them like this, because I don't need any positive y values. I'm not going to be plotting any. And then I need a couple negatives. I'll put the -1 here. A couple positives. I'll put the +1 here. And I need to get all the way to -15. Now, I don't want to squish in 15 tick marks. Excuse me. So I'm going to actually scale by 3s, and then I only have to get 5 tick marks in. We'll do a 6th just for fun. So this is -3, -6, -9, -12, -15, -18. Now, some of you might be going, "Wow, you're breaking your rule you just gave us in the last page." I am, but it's okay in this regard because we're not plotting points and we're graphing a line. So lines are one of the only equations that we can really break this. Now, I've gone by halves here, but if it makes you feel weird, make this a -2 and make this a 2, and now we fixed it and I'm not breaking my rule. So because my numbers are a little squished here, because they're big, I'm going to plot in a different color so it's easier to see. So 0, -12 is right here. 1, -9 is right here. And -1, -15 is right here. And then we just connect the dots. And we've created a nice little line here. But we're not done yet. We need to label our points. We shouldn't have to make anyone guess. This is 1, 9. Excuse me, 1, -9. This is 0, -12. And over here is -1, -15. And whenever you're graphing an equation, make sure you label your equation as well. This is y equals 3x minus 12. So there's our graph of that equation. So now moving on to this next example, we're going to graph this one. We're going to do a little bit of simplifying here. So this is, I'm going to subtract 5 over, we have 3y equals, distributing this 3x plus 6 minus 5, or 3y equals 3x plus 1. Divide everything by 3, and we have y equals x plus 1/3. And then we're going to graph x and y. Now, you may have noticed, and you may already know this, that once we had these 2 points up here on this last example, we didn't really need this third. So you need a minimum of 2 points to form a line. So I can pick just 0 and 1 to figure out what this line is. So 0 is going to give me a 1/3 for y, which gives me the point 0, 1/3. And 1 is going to give me 1 plus 1/3, which is 4/3. So we have 1, 4/3. So here, looking at my y values and my x's, I don't need any negatives really of either of them. Now we will include some negative y's just to make the line look good. But I'm going to make my axes look like this because I don't have any negative x's to plot and I don't have any negative y's, so they can be very easy. I do need to get up to 2 on the y's, and I'll mirror it here just to make it look good. And then 1, 2, 3. Yeah, we'll have the space, so I'll stick the 4 in there. And again, I'll plot this in a different color so it's a little bit easier to see. We plot our points. 0, 1/3 is about right here. Again, it doesn't need to be perfect because we're going to label it in a second. And then 1 4/3. 4/3 is 1 plus 1/3, so that's about here. And then we connect the dots. We label our points. 1, 4/3. 0, 1/3. And our line y equals x plus 1/3. So a couple little things here. When you're labeling your points, the convention is whatever point is closest. Now also make sure you're using a little bit of common sense, and if this says 0, then you know it's the one talking about the point that's on the y-axis. And since this is directly above the 1, you know that that's referring to that one. And again, if your points look a little wonky, like mine usually do, just make them bigger. It'll make it look nice. Okay, so that's our graph there. So the last part of this section is just a few more definitions. So x and y intercepts. These are where the line crosses the x and y axis. To find an x-intercept, we set y equal to 0. And we solve for x. To find a y-intercept, we set x equal to 0. And we solve for y. So kind of opposites, but very, very similar procedures. So we're going to do that in this last example. So we want to find the intercepts and then graph this equation. So we're going to set x equal to 0. So this is 3 times 0 plus 4y equals -12. This is going to go away. 4y equals -12. And then dividing by 4, we get y equals -3. Now this was a choice of a point, so this tells us we have the point 0, -3 as our y-intercept. For the x-intercept, y equals 0. We have 3x plus 4 times 0 equals -12. This is going to go away. 3x equals -12. And dividing by 3, we get x equals -4, which means we have the point -4, 0 as our x-intercept, or x-int. So if you can find your intercepts, these are 2 points. We said in the last example you need minimum 2 points to make a line. So now we can graph these, and since we are graphing just these points, we don't need any positive y's and we don't need any positive x's to plot these on our axes. So I'm going to make my axes look a little different, like this. And then we need to get out to -4 on the x. 1, 2, 3, 4, and I'll put a 5th one just for fun. -2, -4. 1, 2, 3, 4, 5. 1, -2, -3, -4, -5. I don't know why I put those in, so let's put them in here. -5. And then we plot our points. -4, 0. 0, -3. So we have our 2 points and we can make our line. -4, 0, 0, -3, and this is 3x plus 4y equals -12. All right, so you have some options on how you can graph. You can graph by just solving for y, plotting points. You can do a couple more. You need at least 2. You can now graph things from standard form by using your intercepts. Now, we actually did graph this already. Did we? No, we did not graph this already. Losing my mind a little bit. But you can graph with your intercepts or that. So the practice problem in this section is a little bit different. These are some special lines that I want you to take a look at on your own. So you're going to graph them, and then you need to describe the shape, and then talk about why they're unique. But that's the end of 3.1.